Today we're going to talk about production possibilities curves. So before you do anything else, make sure you have downloaded and printed the handout that we're looking at today. There's no way to learn and understand these concepts unless you are actively doing the calculation and doing the graphs along with me. A production possibilities curve, it's another example of a model that we use in economics. And remember, a model is a simplified version of reality that helps us explain some economic concepts or investigate some economic principles. In this case, this production possibilities curve lists, either in a table or as a graph, and we're going to look at it both ways, all of the things that are possible for someone or a country to produce. So it lists all the production possibilities. Now, what we're going to be looking at is Robinson Crusoe. Economists like to use Robinson Crusoe as an example because it does keep things simple. Now, if you're not familiar with Robinson Crusoe, let me tell you a little bit about him. Robinson Crusoe is a fictional character from a book by Daniel Defoe, and it was published way back in 1719. It's an interesting tale about someone who was on a voyage on a ship, and they get stranded on an island all alone. And so this one person, all by himself, has to make all these decisions about how to survive in the wilderness on an island all alone. So that keeps this model simple. We're just dealing with one person and one person's choices about what they would like to produce, given their available resources that they have to work with. So what we're going to focus on here is Robinson Crusoe's energy that he spends collecting food. We're assuming that Robinson Crusoe can either spend his time fishing to get food or collecting some kind of fruit from some trees to get food. And what we're doing in this table is just listing all the possibilities. So I've listed 6 possibilities here, going from A down to F. And the possibilities for Robinson Crusoe, we're assuming here that he's an old man and he can only have the energy to work for 5 hours a day collecting food. So possibility A is when Robinson Crusoe is spending all 5 hours collecting fruit. Possibility F is when Robinson Crusoe is spending all of his time fishing. And B, C, D, and E are all the combinations that you might think of in the middle. 4 hours collecting fruit, 1 hour fishing, for example, for possibility B. So the first thing we're going to do here is we're going to graph all of these possibilities over here on this axis over here. And what we have is on the x-axis we have fish. On the y-axis we're graphing how many fruit. And we just want to visually be able to see what are all of the possibilities that Robinson Crusoe has. So let's start off with possibility A. And possibility A tells us that if Robinson Crusoe spends all of his time collecting fruit, he'll end up with no fish and 20 pounds of fruit. So we graph that first point here. No fish down here on the x-axis, 20 fruit up on the y-axis. There's possibility A. Possibility B, he's spending a little bit of time fishing, so he can get 3 fish, 18 fruit. So 3 fish, 18 fruit. There's possibility B. And what we're going to do is connect all of these points together with a line, and when we're done, we'll have what we call a production possibilities curve. Now you pause the video and graph the rest of these points. So here's what we end up with. Production possibilities curve. Sometimes people will call this a production possibilities frontier. But what are we supposed to get out of looking at this? What visually are we doing that makes this interesting to look at a graph? What we want you to notice is that in most cases in the real world, when you make a production possibilities curve, it's going to have this interesting shape where it's kind of bowed out in the middle, away from the origin, right? So the origin is down here at 0, 0. Production possibilities curves usually aren't straight lines. They're curved, and they're curved out away from the origin. What are the properties of a shape like this that is bowed out away from the origin? Well, what you notice here as we go along from A to F is that this curve looks like it's much flatter up top and much steeper as we get toward D and E and F. And we'll talk about why that is. So it's not enough to know that, okay, that's what it looks like. We need to also understand why that's happening and be able to analyze this very deeply. So we're saying the slope is flat up here, kind of in the middle, and higher, steeper slope as we get down there. Let's actually calculate the slope between each pair of points, and let's talk about what that tells us. Now, in order to do this, let's look at the table first, and let's notice where these numbers come from and dig into them a little deeper, and then we'll look at the slope. When you think about the slope, and we're focusing a lot on the idea of an opportunity cost. Remember, the idea of opportunity cost is what's the best thing you give up when you make a choice to get something else? Here, since we only have two things, fish and fruit, what you give up is always what you're losing, right? So you're always either getting fish and giving up fruit if you make a choice, or you could be getting more fruit and losing fish, one way or the other here. Now, as we move from, say, point A to point B here, what's happening? Well, we're going from 0 fish to 3 fish. So what are we getting? We're getting 3 fish. That's where this number 3 comes from. What are we losing? Well, we're going from 20 fruit to 18 fruit. So we're losing 2 fruit. So we're getting 3, we're losing 2. Let's look at this on the graph and see what that tells us in terms of a slope. So looking at the graph, when we're moving from point A to point B, we can see we're going down 2, right? So what is the slope? It's rise over run. And on this graph, rise means change in fruit, since that's on the y-axis. So I'm going to use the Greek letter delta here, change in fruit. Greek letter delta is shorthand for the word change, so you don't have to write the word change all the time. And what's happening is we're running. We're going over 1, 2, 3. Well, that's the change in how many fish we're getting. So change in fish. So Greek letter delta, triangle, just means change in. So we're going down 2, losing 2 fruit. We're going over 3. And so the slope between point A and B is going to be minus 2 over 3, or minus 2/3. Or we could write that as minus 0.666667, or, kind of round that off if we want to. Now, how does that compare to the slope when we go from E to F? When we go from E to F, we're going over 1. So that means that we're getting 1 more fish. So that's on the bottom, the change in fish, plus 1. And what are we losing? What are we giving up? Well, we're going down 1, 2, 3, 4, 5, 6 fruit. So we're losing 6 fruit. So the slope between E and F is minus 6 over 1, or minus 6. So again, why are we doing all of this? What's the point? Here's what we're learning. Let's just fill in between E and F here, what we were just learning. Fish we get is 1. Fruit we lose is 6. When we talk about opportunity costs, there are a couple of ways we could talk about opportunity cost. One way is I could ask you, what is the opportunity cost of getting these 3 fish? In other words, what did you give up to get these 3 fish? Well, the answer there is obvious. I gave up 2 fruit. That's an easy way to ask and answer that question. Here's a slightly more complicated way. What if I asked you, what is the opportunity cost per fish of each fish that you get? Not of all 3 fish, but what's the opportunity cost of each of the 3 fish individually? On average, how much fruit are you giving up per fish? Now let me give you a little shortcut way of thinking mathematically here. Anytime you say the word per, the word per in English means divide. So when I say per fish, what that in English is telling you to do is divide by fish. Divide by fish. What would the answer be if I asked you, what's the opportunity cost? How many fruit are you giving up per fish? The answer is, take the 2, divide it by the fish, the 3, and the answer is 0.6666 or 0.67 fruit per fish. It's that slope that we just got over here, the minus 2/3, right? Except instead of saying it's negative fruit per fish, the negative is kind of implied because we're saying that you're losing 0.67 fruit per fish that you got. It just means that you're getting more fish than you're losing in fruit. That's why that number's less than 1. So this is the same calculation we did when we calculated the slope. Well, what if we went the other way, though? Right? So here's the next question. What if we went, instead from point A to point B, what if we wanted to go from B back to A and discuss that trade-off? Instead of getting fish and losing fruit, when we move from B to point A here, what we're doing is we're getting fruit and we're giving up fish. If I asked you, what is the opportunity cost per fruit? What is the opportunity cost per each one fruit that you get? That per fruit, per each fruit means divide by fruit. So here we're going to take the 3, divide it by the 2, and we get the 1.5. So what this tells us is that if we want to get fruit by moving from B to A, we're getting only 2 fruit, we're giving up 3 fish. So that means kind of on average we're giving up 1.5 fish for each of those fruit we get if we move in that other direction from B to A. It's just the reciprocal. It's just 1 over the slope, in other words, right? So it's, instead of 2 over 3, it's 3 over 2. So it just depends on how you ask the question. Now, by looking at this visually, looking at this graphically, we're able to see that as we go from A to B to C to D to E to F, things are getting steeper. And that means that the opportunity cost of getting more and more and more and more fish is that we're giving up more and more and more and more fruit for each one because things are getting steeper. So the slope of this production possibilities curve tells us the opportunity cost of each one of these additional fish that we're getting down here on the x-axis. 1 over the slope is telling us the opportunity cost of each fruit if we were going backwards, right? 1 over that slope is kind of the inverse of that relationship. We'll go through one more together. But after we go through this one more together, you pause the video and you fill out the rest of this table and figure out what these opportunity costs are, all right? Let's finish F here first. So we already figured out that between E and F, we're getting 1 fish and we're losing 6 fruit. So what is the opportunity cost of getting that 1 additional fish? Well, it's 6 divided by 1. What's the opportunity cost per each fish? Oh, we're only getting 1 additional fish, right? So we're giving up 6 fruit. That's the opportunity cost. So that's kind of an easy case there. The opportunity cost is 6 per fish, giving up 6 fruit per fish. What would the opportunity cost be of each fruit if we were to go in the opposite direction here? From F all the way back up to E, we're getting 6 fruit and we're only giving up 1 fish for it. That means we're giving up 1/6 of a fish per fruit. And we could write that as a decimal if we wanted to. 0.167 fish given up per fruit gotten. So we're giving up a lot less fish than we are getting fruit. So let's do one more together and then I'll get you to fill out the rest of these. So let's do from B to C. First, let's look at the slope. I think that's the easiest way for me to think about this, but you can find whatever way you think is easiest for you. So when we go from B to C, we see that we're giving up 1, 2, 3 fruit, and we're getting 1, 2.5 fish. We can also see that by looking at the table. Getting 2.5 fish, we're losing 3 fruit. So if we just write those numbers down in the table here, the slope is the opportunity cost of each additional fish. Why? Because the slope tells us rise over run, and when we want per fish, we want to divide by fish, and the run is already the change in fish, right? So we take that 3 divided by 2.5, and our answer is, what is the opportunity cost of each of these additional 2.5 fish that we're getting? 1.2 fruit that we're giving up per fish that we're getting. And we can tell that number has to be bigger than 1 because we're giving up more fruit than we're getting in fish. And what's the opportunity cost if we were to move the other way? From C back to B, we just look at the reciprocal. Instead of 3 divided by 2.5, it's 2.5 divided by 3, which is 0.833. Now, if you're still a little mystified or confused by what we're doing here, let me put this in a different context real quickly. So here is what we analyzed when we were moving from A to B. We're getting 3 fish, we're losing 2 fruit. To make this a little bit more like something you'd think about on a normal day-to-day basis, instead of thinking about fruit we give up, think about it this way. Fruit dollars we pay with. It's like in this situation, if you want the 3 additional fish, it costs you 2 fruit. So instead of thinking about it as giving up 2 fruit, think about that as $2. And the math works out the same as if you were analyzing spending your money at a store. If I were to ask you this question, suppose you bought 3 fish and it cost you $2. And then I asked you this question, what was the cost per fish? Well, the calculation is I got 3 fish and it cost $2. What you always do in these kinds of situations when you're doing this calculation is you put what you get on the bottom of a fraction and you put the cost, what you're giving up, on the top. And so $2 divided by 3 fish tells you that it must have cost you 67 cents per fish. So that's the kind of calculation we're doing. Think about what you're giving up as an amount of money. Perhaps for some of you, that will make a little bit more sense. Now, if we were to flip the scenario, and I said, nope, it wasn't that you were paying with fruit. Suppose you were getting fruit, and you were getting 2 of them, and you were paying with fish. You were trading the fish, paying with fish dollars, for example. Here you can see if you're spending $3 and you're only getting 2 of something for it, they must cost $1.50 a piece. So that's just the kind of calculation we're doing here. So now that you understand that a little better, pause the video and fill out the rest of this table for going from C to D and D to E, and also calculate these opportunity costs over here. And take a minute to tell yourself about what those things mean. So, all right, here's what you should be getting. Now, all this is going into the idea that we really want to make sure we carefully and deeply understand what's happening in this table and in this graph. We understand that the opportunity cost for each fish is going up, up, up as we go down this table, which is the same thing as saying that the slope of this curve is getting steeper and steeper and steeper as we move along this curve. The slope tells us the opportunity cost. Now, why might this be true? Let's look at this important definition, idea, economic principle here that we call the law of increasing opportunity cost. It says that we have increasing opportunity costs when the technology or skills or resources needed for producing 2 different goods are very different kinds of things. This is why the production possibilities curves are curved and not just a straight line. So this opportunity cost tells us how much fruit we have to give up in order to get 1 more fish, and it tells us that that's changing. And it's kind of like the price, like we were talking about before. Now, why does that make sense that these 2 things would have different kinds of resources you need to produce them, and why might that opportunity cost be changing? In order to illustrate that in a little bit clearer way, let's look at another example really quickly here. Now, the classic example of looking at a production possibilities curve looks at a classic trade-off that societies face between spending more money on things like the military, and many times for shorthand, we'll call that guns. So we can spend money having big ships and big bombs and a lot of people in the military, or we can spend money on things that are good for people, things like education and healthcare and housing. And the shorthand we use, don't laugh, but we usually call this butter. And yes, this example goes way, way, way back. People like butter and big government types like guns. Now, I want you to think about, what if we were in an extreme situation here where, we didn't need any guns. There was peace in the world, prosperity, and we were at a point like A here. And let's just say, for the sake of argument, that A is at 100 pounds of butter per person per year, and we're not producing any darn guns. We just don't need them. We're in a period of peace. Now, suppose things aren't so nice anymore, and we needed to move to another point, say point B. As a society, we all got together and we talked about this, and we said, hey, those neighbors of ours are starting to act a little crazy, and it might be in our best interest if we just start spending a little bit of money on some military or defense sorts of things, right? So as a society, we get together and we say, okay, we're not going to go crazy here. Let's just make a few guns. Let's suppose we're going to make, 20 guns. And we do some thinking and calculating, and we say, well, in order to get 20 guns, we might have to give up 8 butter, right? So I'm not saying that number there on the axis is 8, but we're going to give up 8. So we'll go down to, say, 92 units of butter and 20 guns. And we look at that slope, right? So we're getting 20 guns, we're giving up 8 butter. Pretty flat slope there because the opportunity cost is not that high. Who are we going to send? This is the critical question. Now, let's take this literally. Suppose that all we make is butter. So what do we have? Well, we have a bunch of farmers and a bunch of cows and a bunch of people who milk the cows and churn the butter. What kind of person are we going to send from the farm to make the guns? What kinds of people would we want to recruit to send to make these guns? Well, it's going to be 2 kinds of people that we're going to go make the guns. One kind of person might be the worst farmers, people who don't know the right end of the cow to milk, right? So if we send those people to make the guns, we're not going to lose a lot in terms of butter production. The other kinds of people we might send would be the people who are most talented at engineering, right? Maybe the people who are really good at making machinery and putting things together, and the blacksmiths and the people like that. Those are the people we're going to send first. So we're not going to be losing a whole lot of butter, but we're going to be getting a lot of guns by sending just a few of these people to make the guns. Now, we've already sent those people who are the worst farmers and the best engineers to make the guns. Suppose we get a little more concerned about these neighbors of our country, and we decide, hey, we need even more guns. Instead of 20, we want 40. Well, we already have our worst farmers and best engineers on the job. So what are we going to have to send next? Well, we're going to have to send some additional people to make more guns who are a little bit better farmers. They're not our worst. We already sent them. And these additional people we're going to send, so they're not really the worst farmers and they're not really the best engineers anymore. We're going to have to send more people who are better at making butter and who are worse at making guns. So what would we expect to happen when we move to point C? Well, we would expect that we're probably going to have to give up more than 8 butter to get another 20 guns. And so we would expect this next point to represent a little bit steeper decline in butter to get those additional guns. You see the logic here? it might be, let's just look at one more point, to get 60 guns, we would have to send all of our remaining farmers, because the people we're sending are the people who are really good at farming, but people who don't really know the right end of a wrench. So we're not going to be capable of getting a whole lot more guns, but when we move from C to D, what we're doing is we're losing all of the last butter production that we had. So this is the intuition behind this law of increasing opportunity cost here. Because the kinds of skills that we need to produce guns and butter are very different, the trade-offs aren't constant. Now, on the other hand, this implies that if we were talking about producing two goods that were very, very similar, like making guns or making cars, if we assume that we need the similar kinds of factories, similar kinds of knowledge and engineering skills and mechanical skills to make cars as you need to make guns, then a production possibilities curve for those kinds of products could indeed be something more like a straight line that is not bowed out, that does not have increasing opportunity cost. What other kinds of ideas do we need to focus on and learn that we can illustrate from a production possibilities curve here? One thing are some ideas of what we call efficient and inefficient points. So what if I were to suggest to you that today we go out and we work and we come back and we're Robinson Crusoe, and today we're at a point like G. What's happening at a point like G? Well, we're only getting 5 pounds of fish and 5 pounds of berries. What are you going to say to yourself at the end of the day? You're going to say, well, why did that happen? Something must have gone wrong. Because we know from our possibilities, we know that we could get more fish and more fruit, right? So we could get a lot more fish and a little more fruit if we move to a point like E. We could get more of both if we move to a point like D, or a lot more fruit and just a little bit more fish if we move to a point like C. Something's gone wrong. So as a shorthand, we'll call a point like G inefficient. But there's a special way. Now, since economists are efficiency experts, there's a special kind of inefficiency we're talking about when we talk about a point like G. We call a point like G production inefficient. So if you go over here on our handout to this definition B, productive efficiency is the kind of efficiency we're talking about in this chapter. It just means that we're on the production possibilities curve somewhere. It means that we're using our resources efficiently, whatever they are. So efficient points are anywhere A, B, C, D, E, or F, or anywhere in between. It means we're at a point where we can't produce any more using our available resources. Another kind of point we want to think about here is, what about a point like H? We want to call a point like H unattainable. Now, I like to add a word. Textbooks like to just call this unattainable. I like to be a little more optimistic and say, well, this is unattainable today, which means today we only have a certain amount of resources, and H is not possible. Now, we could do a point like F where we get 10 fish but no fruit, but we can't get 10 fish and also 15 fruit, right? Or we could do a point like C where we have 15 fruit but we only have 5.5 pounds of fish. So H is something that we just can't do with our current amount of resources. Now, what kinds of resources does Robinson Crusoe have? Well, he only has himself, and he only has his amount of energy and athleticism that he personally has. But here's why I like to add the word today, because maybe tomorrow Robinson Crusoe could attain some more resources, and tomorrow he could shift this entire production possibilities curve out to where maybe H is something that's attainable in the future, right? So this could be his future PPC, future production possibilities curve, where he's able to produce more. So what are some things that Robinson Crusoe could do today so that in the future he would have higher production possibilities and be able to get to a point like H perhaps? The answer is you need more resources. So we could get more labor. Maybe Robinson Crusoe meets this person called Friday that he meets in the book. Somebody else shows up on the island. Robinson Crusoe, instead of getting more labor, could make his own labor of higher quality. He could start exercising more so that he could work faster or harder or longer. Or he could get better technology. What kind of technology would you like to invent for Robinson Crusoe so that he could do more? Maybe he could make a spear, make a net, make a ladder so that he could get more fruit or get more fish in the amount of time that he has. So more technology or better technology are the keys to economic growth. That's what we're illustrating here when we talk about a shift of a production possibilities curve outward. And the only way to do that is to get more or better quality resources. And the best way to think about doing this is by investing today so that you can have more productive resources in the future. So it'll cost you something today, but in the future you can be more prosperous if you're smarter or healthier or have better technology to work with. Now there's another kind of efficiency that I'd like to talk about here, and that's allocative efficiency. We already talked about economic growth here a second ago. Allocative efficiency is a different kind of efficiency, and it focuses on the idea not just asking the question, are we producing as much as we can? That's productive efficiency, right? We're producing some combination that is as much as we can. Allocative efficiency asks the question, are we producing the correct combination of outputs? And by the correct combination of outputs, I mean, what combination of fish and fruit is going to make Robinson Crusoe as happy as possible? What are we going to be able to do to maximize his utility? So we're saying, okay, Robinson Crusoe, not just are you on the production possibilities curve somewhere, but are you at the point A, B, C, D, E, or F, or somewhere in between? That is the point that makes you happiest. So which one is the best point? The answer is we have no idea unless we ask Robinson Crusoe himself, because everyone has different preferences. Everybody likes different things in different ways. Let me tell you that if I were Robinson Crusoe, point A would be the one that would be allocatively efficient to me. Allocatively efficient just means, are we allocating our resources in the right direction? Do we need a lot of fruit or a lot of fish? Well, for me, I would want all fruit, just because I hate fish. I'm not a huge fruit fan, by the way, but depends on the kind of fruit. But for me, A would be the best. But for everybody in this class, you would have a different answer depending on your preferences. Now, if you want to end this video here, I don't blame you. But I'm going to spend another few minutes going through a brief example that will really help you when we get into chapters 2 and 3 and 4 and help you understand the basic idea of economics, which is decision making. Investigating this idea of allocative efficiency a little deeper will help that, and I'll try to be very brief here. Let's ask Robinson Crusoe very briefly what he does like. Let's ask him about his preferences. And this is the clearest way you can ask someone about their preferences, is to ask them these kinds of questions. So the production possibility curve tells us about the cost of making different choices. What's the opportunity cost? Or how many fruit is Robinson Crusoe giving up to get each additional fish? That's what that opportunity cost is telling us about. But let's ask about the benefits, because after all, economics is all about weighing the costs and the benefits to make the right choice. So let's ask Robinson Crusoe about the benefits. The way to ask people about benefits is to ask them about how much they value things in terms of some other thing. The easiest way is to ask people about how much they value something in money terms, but today, since we're talking about fruit and fish, we're going to ask Robinson Crusoe how much he values each fish. So Robinson tells us something like, if I had no fish at all, I'd be willing to trade or give up 10 fruit to get a fish. But if I had one fish, I'd only be willing to trade 9 fruits to get a second fish. Your willingness to give up fruit is going to go down as you already have more and more and more fish. And he says if I had 2 fish, I'd be willing to give up 8 fruit to get a third fish. If I already had 3, I'd only be willing to trade 7 fruit to get a fourth fish, etc. Now what I've done over here on this graph is I've already graphed the opportunity cost of getting additional fish based on the calculations that we made up above. Don't worry too much about exactly how I graphed it. Just trust that what I'm doing here is graphing those opportunity costs we calculated. The 0.67, the 1.2, 2, 3.33, and the 6 from up here. Now, if we also graph Robinson Crusoe's responses, where he told us that he'd be willing to trade 10 fruit to get the first fish, 10 fruit to get 1 fish, and that he's willing to trade 9 fruit to get a second fish, and 8 fruit to get a third fish, and 7 fruit to get a fourth fish, and 6 and 5 and 3 and 1. And then he says, if I already had 8 fish, I don't want any more fish. Okay, so if he already had 8 fish, he's telling us he wouldn't give up anything to get a 9th fish. So his willingness to give up fruit for the 9th fish would be 0. What we've graphed here is the marginal cost of each fish, the additional cost of getting each additional fish, compared to the marginal benefit, the value to Robinson Crusoe of getting each additional fish. And what you want to do, this is a general principle in economics, is that as long as the additional benefit or willingness to give up fruit is higher than the additional cost of getting fish, you want to keep on going. You want to keep on fishing and fishing and fishing. And Robinson Crusoe's optimal point, where he would want to stop fishing and then leave and go start collecting fruit, would be at this point where these 2 lines intersect. And just to make that a little more explicit, he's willing to get the first fish because he's willing to give up 10 fruit to get the first fish. But he only has to give up 2/3 of a fruit to get the first fish. Along here in the middle, he's willing to give up 8, 7, or 6 fruit to get the 3rd, 4th, and 5th fish. But in this region, he's only having to give up a little more than 1 fruit to get each fish. And where he should stop is where these 2 lines intersect. He shouldn't keep going because over here, he has to give up 6 fruit to get that last fish, but he's willing to give up nothing to get that last fish. So that would be an indication that he just did something wrong. So this is an example of marginal decision making and trying to figure out when you should stop doing something. If you don't completely get that last bit, as I say here on the handout, this is advanced material, but if you sort of understood the logic there, it's going to go a long way toward helping you understand a lot of the things that come next in this class. So think about it a little bit, see if you understand it. If not, don't panic. This is Dr. Berkey signing out. I wish you the best of luck.